The James Webb Space Telescope looked deeper into the universe than anything before it, and what it found did not look young. It found galaxies that already seemed finished. Massive structures, glowing with billions of stars, arranged in shapes that take time to build, appearing at a moment in cosmic history when time itself had barely begun to pass. They weren't forming, they weren't emerging, they were already there. It was like turning to the very first page of a book and realizing the story was already halfway written. For a long time, the early universe was imagined as something fragile, place of beginnings. After the Big Bang, everything expanded rapidly, cooling into darkness. There were no stars yet, no galaxies, no structure. Just a vast, thin sea of particles, almost perfectly uniform, with only the slightest imperfections scattered within it. Those imperfections mattered. Over immense stretches of time, gravity would begin to pull them together. Slowly, relentlessly, patiently, tiny clumps would grow into larger ones. Gas would collapse inward, pressure would rise, and eventually the first stars would ignite. Not all at once, but here and there, like distant sparks in an endless night. Those first stars would live quickly. They would burn intensely, collapse violently, and scatter heavier elements back into space. Only after generations of these stars lived and died would galaxies begin to take shape. It was not a fast process. It was something that unfolded gradually, almost quietly, across hundreds of millions of years. At least that was the picture. But when Webb began sending back its deepest images, that picture started to feel incomplete. Because instead of faint, irregular fragments, astronomers kept seeing something else. Galaxies that looked far too developed, not just slightly ahead of schedule, but dramatically so. Some of them appeared large enough to rival galaxies that should have taken billions of years to assemble. They weren't chaotic clouds. They had structure, shape, density. They looked settled, and they were appearing incredibly early, so early that, according to current models, there simply shouldn't have been enough time for them to exist in that form. It wasn't just one object. It wasn't even a rare anomaly. They kept showing up, again and again, in different regions of the sky, at different distances, telling the same quiet, unsettling story. The early universe did not look as slow as we thought. For a moment, imagine standing there, not here on Earth, but suspended in that ancient era. The universe is still young. There are no familiar galaxies yet, no long-established structures stretching across space. Everything should feel new, unfinished, and yet, in the distance, there they are. Vast islands of light, stable, bright, fully assembled, as if they had skipped the beginning entirely. There is a strange silence in that realization, like hearing an echo before the sound that caused it. So the question began to form, not loudly, but persistently. How did they grow so fast? Because to build a galaxy, you need stars, a lot of them, and to build stars, you need gas collapsing under gravity, cooling, fragmenting, igniting. Every step takes time. Time to gather matter. Time for gravity to pull it together. Time for stars to form, evolve, and influence their surroundings. There are limits to how quickly this can happen, or at least, there were supposed to be. One possibility is that these galaxies only appear more massive than they truly are. Light, after all, can be deceptive. As it travels across billions of years, it stretches, it dims, it shifts into wavelengths that require careful interpretation. Perhaps what we are seeing is not their true size, but an illusion created by distance and time. But even when accounting for those effects, many of these galaxies still seem too large, too bright, too real. Another idea is that star formation in the early universe was far more efficient than we expected. Maybe the conditions shortly after the Big Bang allowed gas to collapse much faster. Maybe stars formed in bursts of incredible intensity, converting matter into light at a rate far beyond what we see today. In that case, galaxies could grow quickly, compressing what should take hundreds of millions of years into a much shorter period. But this raises another problem. If stars formed that quickly, what stopped them? Why doesn't the universe still behave that way? There is also the possibility that something more fundamental is missing, that our understanding of how structure forms, how gravity operates on these scales, or how matter behaved in the earliest moments of the universe is not complete. Not wrong necessarily, but incomplete, like trying to reconstruct a story with entire chapters missing. And as astronomers continued to analyze the data, the discomfort didn't fade, it deepened, because the more carefully these galaxies were studied, the harder they became to dismiss. Their light carried signatures of complexity, elements that should not yet have been abundant, structures that implied long histories of formation and change. Histories that, according to the timeline, had not yet happened. It is a quiet kind of contradiction, not explosive, not obvious, but persistent, like noticing something slightly out of place, and realizing the longer you look at it, the less it makes sense. And then, as if that weren't enough, another detail began to emerge, because some of these early galaxies didn't just look massive. They appeared to contain something even more difficult to explain. At their centers, there were signs of enormous black holes, objects so dense, so extreme, that even light cannot escape them. And somehow, they too seem to be there, far earlier than expected. If galaxies are growing too fast, and black holes are appearing too soon, then the question becomes deeper. Not just how did this happen, but what else in the early universe is not what we thought it was? Somewhere out there, in the faintest light ever detected, the universe is telling a different story, and we are only just beginning to hear it. Then there were the black holes. At first, they appeared as subtle distortions in the data, unusual brightness, energy signatures that didn't quite match what a normal galaxy should produce. But as observations improved, the picture became clearer. Some of those early galaxies, the same ones that already seemed too large, too evolved, were not just collections of stars. They were feeding something. At their centers, something immense was already there. Black holes are not supposed to form instantly. Even the simplest explanation requires time. A massive star must first live, then die, then collapse under its own gravity, leaving behind a dense core. That core can grow, slowly pulling in surrounding matter, increasing in mass over millions, sometimes billions of years. That is the normal path. That is the expected path. But what Webb began to hint at did not follow that path, because some of these black holes appeared to be enormous, not just slightly larger than expected, but already comparable to the giants we see in much older galaxies. It was like finding a seed and realizing it was already a towering tree. For a moment, imagine the scale of what that means. A black hole with millions, even billions, of times the mass of our sun, existing when the universe itself had barely begun to age. There shouldn't have been enough time, not for stars to form in the numbers required, not for them to collapse, not for the black hole to grow to that size. And yet, the light suggests they are there, quietly consuming matter, shaping the galaxies around them as if they had always been part of the story. So again, the explanations begin. One possibility is that these black holes formed differently. Instead of growing slowly from dying stars, perhaps some of them collapsed directly from enormous clouds of gas, skipping the usual steps entirely. In that scenario, a black hole could form much more quickly, already massive from the very beginning. But even that idea has limits. It requires very specific conditions, and it's still unclear whether those conditions could have been common enough to explain what we're seeing. Another idea is that black holes in the early universe simply grew faster, that they consumed matter at extreme rates far beyond what we observe today. In the dense, chaotic environment of the young cosmos, there may have been more material available, more collisions, more fuel. Galaxies might have fed their centers aggressively, pouring gas inward, allowing black holes to expand rapidly. But this too raises questions. If they were growing that fast, why don't we see similar behavior now? What changed? And then there is a more unsettling possibility, that these black holes did not grow inside galaxies, but alongside them, or even before them. that in some cases the black hole may have come first, a gravitational anchor pulling matter inward, forming the galaxy around itself. It reverses the story. Instead of galaxies creating black holes creating galaxies. And if that is even partially true, then the structure of the universe itself may not have unfolded in the way we imagined. There is a strange stillness in that idea, because it suggests that in those earliest moments, the universe may not have been building upward slowly, but assembling itself around invisible centers, hidden engines already in place. And yet, even this does not fully resolve the tension, because when astronomers look closer, they don't just see large black holes. They see something else, something equally difficult to explain. The light coming from these early galaxies contains elements that should not yet exist in large amounts. Carbon, oxygen, nitrogen. These are not primordial elements. They are forged inside stars, created over generations of stellar life cycles. A star forms, burns, dies, and in that death, it enriches the surrounding space. That enriched material then forms new stars, which continue the process. Takes time, repeated cycles, a kind of cosmic recycling. But in these early galaxies, that process seems to have already happened. Not once, but many times, enough to leave clear signatures in the light we observe today, which means, somehow, stars must have lived and died over and over again in a window of time that should have been far too short. It is like walking into a room that was just built and finding layers of dust already settled on every surface. Evidence of time passing before time should have had the chance to pass. So the questions begin to overlap. Galaxies forming too fast, black holes growing too quickly, elements appearing too early. Each one on its own is difficult. Together, they begin to form a pattern, a quiet suggestion that the early universe was not as simple or as slow as we once believed. And as Webb continues to look deeper, further back, closer to the beginning, the boundary between what we expected and what we observe begins to blur. Because if the first galaxies were already mature, if black holes were already massive, if stars had already lived entire lifetimes, then the question is no longer just about how fast things formed. It becomes something deeper. What if the universe didn't start as slowly as we thought? What if the first chapters were not quiet, not gradual, but filled with rapid, intense bursts of creation? Moments where structure appeared quickly, almost abruptly, before settling into the slower evolution we see today. Or perhaps we are only seeing part of the story, fragments of light that hint at processes we don't yet fully understand, hidden phases of cosmic history that unfolded differently than our models predict. And somewhere within that uncertainty, there is a quiet realization that the deeper we look, the less familiar the universe becomes. Because this wasn't just about galaxies, or black holes, or early stars. It was about the timeline itself, and whether the sequence we've trusted, from simplicity to complexity, from chaos to structure, is truly as straightforward as it seems. And if it isn't, then what else, hidden in that ancient light, is waiting to be understood? There is another detail, one that is easier to overlook at first, but becomes harder to ignore the longer you sit with it. Because it is not just what Webb is seeing, it is how far back it is seeing it. When we observe distant galaxies, we are not seeing them as they are now. We are seeing them as they were. Their light has been traveling for billions of years, crossing an expanding universe, stretching, fading, until finally, it reaches us. To look deep into space is to look deep into time. Some of the galaxies Webb has detected existed when the universe was only a few 100 million years old. A brief moment on a cosmic scale, less than a fraction of its current age. And yet, within that narrow window, something seems to have accelerated. Because the deeper we go, the more crowded the universe appears. Not empty, not quiet, but filled with galaxies, with structure, with light. This is where the tension deepens, because according to the Standard Model, the earliest universe should have gone through a period often called the Cosmic Dark Ages, a time before stars had fully ignited, before galaxies had fully assembled, a long stretch of darkness where matter existed, but light had not yet taken hold. And yet, that darkness seems shorter than expected, almost as if it was skipped or compressed. Instead of a long, gradual awakening, Webb's observations suggest something more abrupt, as if the universe didn't slowly turn on the lights, but did so in bursts, pockets of sudden brightness, appearing earlier and more frequently than we thought possible. Imagine walking into a vast, dark city at night. You expect silence, empty streets, dark windows, but instead, lights are already on. Not everywhere, but in enough places to change the feeling entirely. You can see structure, movement, life, even though, by all expectations, it should still be asleep. This is what the early universe is beginning to feel like. Not fully formed, but not truly dormant either. Something in between, something faster. So astronomers began to reconsider the timeline. Perhaps the first stars formed earlier than expected. If that happened, even by a small margin, could cascade forward. At first, this seemed like a helpful tool, a way to look even deeper, to see even earlier. But over time, it introduced another layer of uncertainty. Because if light can be magnified, can also be misleading. Some of the earliest galaxies detected by Webb appear brighter than expected, more massive, more developed. But if their light has been stretched and amplified by gravitational lensing, then their true nature becomes harder to determine. Are we seeing them as they really are, or as they appear through a cosmic distortion? Astronomers began to carefully analyze this, mapping the foreground galaxies, studying the way light bends around them, trying to reconstruct the original image. In some cases, lensing could explain part of the discrepancy, making galaxies appear larger or brighter than they truly are. But not all of it. Even after accounting for these effects, many galaxies still seem too massive, too luminous, too mature. It's like looking through a warped piece of glass. At first, you assume the distortion explains everything. But then you adjust your view and realize the object itself is still unusual. So the mystery remains. And then there is something even more subtle, something that doesn't immediately stand out, but becomes more significant the longer it is studied. The distribution of these galaxies. They are not randomly scattered. They begin to show patterns, clusters, filaments, structures forming across vast distances. This is not unexpected on its own. In the modern universe, galaxies are arranged in a kind of cosmic web, connected by invisible strands of dark matter. But seeing hints of that structure so early raises another question. How did the universe organize itself so quickly? Because building large-scale structure is not simple. It requires matter to move, to gather, to settle into patterns over time. Gravity must act across enormous distances. Small fluctuations must grow, amplify, and eventually shape the distribution of galaxies. This process takes time, a lot of time, and yet there are signs that some of that structure may already have been emerging earlier than expected, not fully formed, but present enough to be noticeable. It is like seeing the outline of a vast network before the individual pieces have fully developed. A faint blueprint already in place. So now the questions begin to stack. Galaxies forming too early, black holes growing too fast, stars evolving too quickly, elements appearing too soon, and now, structure itself, taking shape ahead of schedule. Individually, each one could be explained, adjusted, refined, but together, they begin to lean in the same direction, towards something deeper, a possibility that the early universe was not simply a slower, simpler version of what we see today, but something fundamentally different, perhaps the rules themselves were not exactly the same, not entirely different, but shifted subtly. Conditions may have existed in those first moments that allowed matter to behave in ways we no longer observe. Faster collapse, more efficient cooling, more intense interactions, a kind of brief window where the universe operated under slightly different circumstances. And if that window existed, it may have left behind exactly what we are now seeing. Galaxies that appear too early, structures that form too quickly, a timeline that feels compressed, but proving that is not simple because we cannot go back. We cannot observe those moments directly. All we have is the light, faint, ancient light, carrying fragments of information across unimaginable distances. And we have our models, our simulations, our attempts to recreate the universe from its earliest moments. But every model is only as complete as the assumptions behind it. And right now, those assumptions are being tested. Quietly, relentlessly, with every new observation, the universe offers another piece of the puzzle. Sometimes it fits, sometimes it doesn't, and sometimes it suggests the picture itself may need to change. There is a strange kind of calm in that realization, not knowing, but continuing to look, because the deeper we go, the more the universe reveals, not answers, but possibilities. And somewhere within those possibilities, there may be an entirely new way to understand how everything began. But if that's true, then what we've seen so far may only be the surface, because beyond these galaxies, beyond these structures, there are still deeper questions. Questions about what existed before the first stars, before the first light, before anything we can currently observe. And if the early universe is already this strange, then what lies even further back may be stranger still. And yet, even deeper than galaxies, even deeper than black holes, there is another layer to this mystery. One that doesn't glow, one that doesn't emit light at all, because most of the universe is invisible. Everything we've been talking about, stars, galaxies, glowing gas, that's only a small fraction of what actually exists. The rest is something we cannot see directly, something that does not shine, does not absorb light, does not interact in ways we can easily detect. Dark matter, it surrounds galaxies, holds them together, shapes the large-scale structure of the cosmos. Without it, galaxies as we know them wouldn't exist. They would spin themselves apart. And yet, we still don't know what it is. We only know how it behaves. It moves through space, responding to gravity. It gathers into vast halos, invisible frameworks, within which galaxies form. So when we look at the early universe, we are not just looking at stars and galaxies forming. We are looking at dark matter, doing something, and that something may be more important than we realize. Because if galaxies are appearing too early, then the structures guiding their formation, those dark matter halos, must have formed early too, earlier than expected, which raises a quiet but unsettling possibility. What if dark matter itself was behaving differently in the early universe? Not dramatically different, not in a way that breaks everything we see today, but just enough to accelerate the process. Imagine a landscape forming beneath the surface, invisible hills and valleys, guiding the flow of everything above. If that landscape formed faster, or became more pronounced earlier, then everything built on top of it would follow. Galaxies would gather sooner, stars would ignite earlier, structure would emerge faster. It would explain, at least in part, what Webb is seeing. But again, this opens another layer of uncertainty, because dark matter has been studied for decades. Its effects are consistent across the universe, from galaxy rotation to gravitational lensing to the large-scale structure of the cosmos. Changing its behavior, even slightly, in the early universe would ripple through everything. And yet, that may be exactly what the data is hinting at. Some models suggest that dark matter could have been colder or clumpier at earlier times, meaning it would gather more efficiently, forming dense regions of gravity much sooner. Other ideas propose interactions we haven't yet detected. Subtle forces, acting only under specific conditions, allowing dark matter to collapse faster. In those first moments, these are not confirmed. They are possibilities, careful attempts to reconcile what we see with what we think we understand. But there is another possibility, one that is harder to test and more difficult to accept, that dark matter is not the full story, that there may be additional components, hidden aspects of the universe that only reveal themselves under extreme conditions. Conditions like the early universe. It's a quiet thought, but a powerful one, because if there is something else, something we have not yet accounted for, then everything built on top of it, galaxies, stars, black holes, would reflect that hidden influence. And what we're seeing now could be the first hint of it, a subtle imprint left behind in the oldest light. There is a certain stillness in considering that idea, that the universe, even now, may contain layers we haven't uncovered, not because they are far away, but because we don't yet know how to see them. And yet, Webb is changing that. By looking deeper, by capturing light that has traveled longer, by revealing structures that should not yet exist, it is forcing us to confront those hidden possibilities, not directly, but indirectly, through inconsistencies, through patterns, through quiet contradictions that refuse to go away. And as those contradictions grow, they begin to point somewhere, not to a single answer, but to a direction, a suggestion that the early universe was more complex, more dynamic, and perhaps more unfamiliar than we ever imagined. And if that is true, then everything we've seen so far, the galaxies, the black holes, the early structure, may only be the visible surface of something deeper, because beneath it all, there may be processes, forces, or components that we are only just beginning to sense. And the deeper Webb looks, the more those hidden layers seem to press against the edges of what we understand, quietly, relentlessly, as if the universe is not just revealing itself, but slowly reminding us that we have only just begun to see it clearly. And if even the invisible parts of the cosmos may not behave the way we expected, then the question becomes deeper still. What else, in those earliest moments, was not what it seemed? And if that question feels distant, almost abstract, there is something else Webb has seen that feels far more immediate, because some of these early galaxies should not even be visible, not clearly, not in the way we are seeing them now. The early universe was not transparent. After the first light appeared, after the first stars ignited, the universe was still filled with a dense, neutral fog of hydrogen, a kind of cosmic haze. It absorbed light, scattered it, prevented it from traveling freely. So even if galaxies existed, their light should have struggled to reach us, dim, distorted, barely detectable. And yet, Webb is seeing them clearly, which suggests something else happened, something that changed the state of the entire universe. Reionization, a slow transformation where that neutral hydrogen became ionized, allowing light to pass through space freely. It is one of the most important transitions in cosmic history. Without it, the universe would remain opaque, dark, unobservable. But here is the problem. This process should have taken time, hundreds of millions of years, a gradual clearing of the fog, as more and more stars formed, emitting radiation strong enough to ionize the surrounding gas. A slow dawn, but what Webb is seeing doesn't fully match that timeline, because these galaxies, they are not just present, they are visible, which means by the time their light began its journey, the fog was already lifting, earlier than expected, and that creates another quiet tension in our understanding, Because if the universe became transparent sooner, then something must have driven that process faster, something powerful enough to change the state of space itself. One idea is simple: more stars. If early galaxies formed faster, then they would produce more radiation, accelerating reionization, a chain reaction. More galaxies, more stars, more light, faster clearing. It fits, but only if those galaxies are as numerous and as active as they appear, and even then pushes the limits of what our models allow. Another possibility is that the first stars were different, not like the stars we see today, larger, hotter, more intense, capable of emitting enormous amounts of high-energy radiation, enough to carve out clear regions in the cosmic fog, much earlier than expected. These are sometimes called population 3 stars, the very first generation, made almost entirely of hydrogen and helium, no heavy elements, no metals, which may have allowed them to grow to extreme sizes, burn brighter, and live shorter lives. If they existed in large numbers, they could have transformed the early universe much more rapidly. But here's the problem: we haven't directly seen them, not yet. They remain theoretical, inferred from models, suggested by indirect evidence, but never clearly observed. And yet, their existence would help explain what Webb is seeing. So again, we are left in a familiar place, between observation and explanation, between what is visible and what is understood, because the universe is not just showing us something new, it is showing us something that doesn't fully align with the story we've been telling. Not completely wrong, but incomplete, as if key pieces are still missing, and those missing pieces are starting to matter, because when you combine everything, early galaxies, unexpected structure, possible shifts in dark matter, and now a universe clearing its fog sooner than expected, you begin to see a pattern, not a contradiction, but a pressure, a subtle push against the boundaries of our current understanding. And that pressure is coming from the very beginning of time, from an era we thought we had mostly understood, an era that now feels less certain, less settled, as if the early universe was not a simple, gradual unfolding, but something more complex, more accelerated, more precise. And if that's true, then everything that followed, every galaxy, every star, every structure we see today, was shaped by conditions we may not yet fully grasp, which brings us back to a deeper question, not just how the universe evolved, but how it began to take shape in the first place. Because if even the fog of the cosmos lifted earlier than expected, then the forces driving that change may have been set from the very beginning, and whatever those forces were, they may still be influencing the universe today, quietly, in ways we are only now starting to notice. Then, if all of this traces back to the very beginning, we have to go further, not to galaxies, not to stars, not even to dark matter, but to the moment before any of it existed, in the form we recognize. The early universe, just after the Big Bang, was not structured. It was not filled with galaxies waiting to form. It was something far more uniform, almost perfectly smooth. Energy spread out evenly, with only the smallest variations, tiny fluctuations, differences so small that for a long time they were almost ignored. But those tiny fluctuations changed everything, because they became the seeds of all structure, every galaxy, every cluster, every filament stretching across the cosmos. All of it grew from those initial differences. And here is where things become quietly unsettling, because those fluctuations were not random in the way we might expect. They had a pattern, a distribution, one that fits remarkably well with a very specific idea: cosmic inflation, a moment In the earliest fraction of a second, when the universe expanded, faster than the speed of light, not objects moving through space, but space itself, stretching rapidly, exponentially, taking something incredibly small and expanding it to cosmic scales. In that process, quantum fluctuations, microscopic variations, were stretched outward, becoming the blueprint for everything that followed. It's an elegant idea. It explains why the universe looks so uniform on large scales, why those fluctuations have the specific pattern we observe, and for decades, it has matched our data with remarkable precision. But now, there is a quiet tension, because if inflation created the initial conditions, and those conditions determined how quickly structure could form, then the timing we are seeing now matters a lot. If galaxies are forming earlier, if structure is appearing faster, then either those initial fluctuations were slightly different or something after inflation amplified them. Even a small change at that stage would ripple forward through billions of years, leading to a universe that looks subtly, but importantly, different. And that difference may be what we are starting to see. Some researchers have begun asking a careful question: what if inflation was not as simple as we thought? Not a single, smooth event, but something more complex. Perhaps it had phases, moments where the expansion rate changed, even slightly, creating variations in how those initial fluctuations were distributed. Tiny imprints left behind at the very beginning, too subtle to notice at first, but powerful enough to influence how quickly matter began to gather, how fast gravity could take hold, and ultimately, how soon galaxies could form. There are even models that suggest inflation may not have been perfectly uniform across all regions of space, that some areas could have experienced slightly different conditions, leading to pockets of the universe where structure forms earlier or later than average. If that's true, then what Webb is seeing might not be a contradiction. It might be a glimpse into one of those regions, a place where the early conditions were just different enough to accelerate everything. But again, this is not confirmed. It is a possibility, a careful extension of what we already believe, because changing inflation is not a small adjustment. It sits at the foundation of modern cosmology. Touching it means rethinking how the universe itself began to take shape, and yet the data is pushing us in that direction, not loudly, but persistently, through patterns that don't quite align, through observations that arrive just a little too early, through structures that seem just a little too developed. Each one, on its own, can be explained, but together, they begin to suggest something deeper, that the earliest moments of the universe may hold more complexity than our current models capture, more nuance, more structure, more influence over everything that followed. And if that's true, then the story of the universe doesn't begin with simple uniformity, slowly breaking apart. It begins with subtle differences already in place, quiet imbalances guiding everything forward from the very first instant, which means what we are seeing now, these early galaxies, this accelerated structure, may not be anomalies. They may be echoes of conditions set at the very beginning, conditions we are only now starting to uncover. And if inflation itself left behind more than we expected, then somewhere hidden within the structure of the cosmos, there may still be traces of that moment, encoded in the way galaxies form, in the way matter gathers, in the timing of everything we are now observing. And Webb, without ever looking directly at that first instant, may already be revealing its consequences quietly through a universe that seems to have begun just a little differently than we imagined. And if those first moments left behind subtle imprints, then there is one place we can still look to see them directly, not in galaxies, not in stars, but in light, very old light, the oldest light we can possibly observe, the cosmic microwave background, a faint glow filling the entire universe, not coming from any single source, but from everywhere. It is the afterglow of a time when the universe first became transparent, long before galaxies formed, long before structure emerged, when everything was still in its earliest state. And for decades, this light has been one of our most powerful tools because it carries information from that distant time, encoded in tiny variations of temperature, fluctuations so small they are measured in millionths of a degree, but those tiny differences map directly to the initial fluctuations we talked about before. They are the earliest blueprint of the universe we can actually see, and until recently, they have agreed almost perfectly with our models. But now, as Webb reveals a universe that seems to evolve faster, those patterns take on new meaning, because if something was different in the beginning, then traces of that difference should still exist in this ancient light, subtle, almost impossible to notice without knowing what to look for. Some scientists are now re-examining this cosmic background, not to confirm what we already know, but to look for what we might have missed, tiny anomalies, slight asymmetries, patterns that don't quite fit, the simplest version of inflation, nothing dramatic, but enough to raise questions, because even a small deviation could help explain everything we're seeing now: earlier galaxies, faster structure, unexpected complexity, all of it tracing back to those first imprints. There are hints, very faint ones, that the universe may not be perfectly uniform on the largest scales, that there might be preferred direction, a slight imbalance in how fluctuations are distributed. Some have called it a cosmic axis. Others remain cautious because these signals are incredibly subtle, close to the limits of what we can measure, but they exist. And in light of Webb's discoveries, they are being taken more seriously, because what once seemed like statistical noise may now be part of a larger pattern, a connection between the earliest light and the earliest structure, between the beginning and what followed, much sooner than expected. If that connection is real, then we are not just observing separate mysteries, we are seeing different pieces of the same story, a story where the universe was never perfectly simple, never perfectly uniform, but carried subtle variations from the very start, variations that quietly shaped everything, from the distribution of matter to the timing of galaxy formation to the structure we now observe billions of years later. And what makes this so powerful is that it connects two completely different observations, one from the oldest light in the universe, the other from some of the earliest galaxies ever seen, separated by hundreds of millions of years, and yet possibly linked by the same underlying cause. That kind of connection is rare, and when it appears, it often means we are getting closer to something fundamental, not a small adjustment, but a deeper understanding of how everything fits together. Because if the cosmic microwave background already contains hints of these differences, then Webb is not discovering something entirely new. It is revealing the consequences of something that was always there, something we saw but did not fully understand until now. And that changes how we think about discovery, because sometimes the universe doesn't hide things by keeping them far away. It hides them in plain sight, in data we already have, in patterns We thought we understood, waiting for a new perspective, for a new observation to give those patterns a different meaning, and that may be what is happening now, a quiet shift where old data and new observations begin to align in a way they never have before, pointing not to a single answer, but to a deeper question. What if the universe was never as simple as our models suggested? What if complexity was there from the very beginning, and what we are seeing now is not the universe changing, but us finally beginning to notice it? And if that is true, if the complexity was always there, then the next question becomes unavoidable. Why? Not just how the universe formed, not just how structure appeared so early, but why the conditions allowed it to happen this way. Because when we look at everything together, the timing, the structure, the early transparency, the subtle imprints in ancient light, it begins to feel precise, not perfectly tuned, but balanced, in a way that allows complexity to emerge quickly. And that brings us to something deeper, the laws themselves, the fundamental rules that govern everything: gravity, energy, expansion, the behavior of matter, all of it set at the very beginning, and all of it working together to shape what we now observe. Because even small changes to these laws would lead to a very different universe. If gravity were slightly weaker, matter would take longer to gather. If expansion were slightly faster, structures might never form at all. If conditions in the early universe were even slightly different, the timeline we are seeing now would not exist. And yet, it does, which raises a quiet possibility that what we are observing is not just the result of random conditions, but of constraints, limits, within which the universe can exist and still produce structure. Some scientists describe this through the idea of the anthropic principle, the notion that the universe must be compatible with the existence of observers, not as a purpose, but as a condition, because if the laws were different, we wouldn't be here to notice them. It's a subtle idea, and often misunderstood. It doesn't explain why the universe exists this way, but it does remind us that not all possibilities are equally likely to be observed. Still, that alone doesn't fully address what Webb is showing, because this isn't just about existence. It's about timing, about how quickly complexity emerges. And that leads to another possibility, that the universe may allow for a wider range of outcomes than we expected, that under the same basic laws, structure can form earlier, faster, more efficiently, depending on initial conditions we are only beginning to understand. In that sense, what we are seeing may not be improbable, just unfamiliar, outside the range of what we assumed was typical. But there is also a more speculative idea, one that sits at the edge of physics, that our universe may not be the only one, that there could be a larger framework, a multiverse, where different regions or different universes have different initial conditions, different fluctuations, different outcomes. In such a picture, some universes would form structure slowly, others more quickly, and we would naturally find ourselves in one where complexity is possible. Again, this is not confirmed. It is an extension, a way of thinking about why conditions might vary. But what makes Webb's observations so interesting is that they gently push us toward these deeper questions, not because they demand radical answers, but because they expose the limits of our current ones. And that is where science often changes direction, not in moments of complete contradiction, but in moments of quiet discomfort, where the data still fits, but not perfectly, where explanations still work, but feel incomplete, where something subtle keeps returning, and that subtlety is what we are seeing now, because nothing we've observed has broken the universe, still follows rules, still behaves consistently in most ways, but at the edges, at the earliest times, at the deepest levels, there are hints that the story is not finished, that there are layers we have not yet uncovered, and that those layers may hold the key to understanding why everything unfolded the way it did, from the first fluctuations to the first stars, to the first galaxies, all the way to what we are now observing with Webb, and perhaps to something even deeper, because when we ask why, at this level, we are no longer just studying the universe, we are exploring the boundaries of explanation itself, what can be known, what can be tested, and what may always remain just beyond reach. Yet even there, the universe leaves clues in patterns, in timing, in structure, and now, through Webb, those clues are becoming clearer, not enough to give us final answers, but enough to show us where to look next. And sometimes that is how understanding begins, not with certainty, but with direction. And now, after all of this, after galaxies appearing too early, after structure forming too fast, after light traveling through a universe that should still be opaque, we arrive at something unexpected, not a conclusion, but a boundary, the edge of what we can currently explain. Because every idea we've explored, dark matter, reionization, inflation, the earliest fluctuations, even the fundamental laws themselves, they all still work, just not perfectly, not in a way that fully accounts for what Webb is showing. And that matters, because in science, this is often where things begin to change, not when everything breaks, but when everything almost works, when the picture is nearly complete, but small details refuse to fit, details that seem minor at first, a galaxy that forms a little too early, a structure that appears a little too developed, a signal that arrives a little too soon, each one easy to explain on its own, but together they form a pattern, a quiet accumulation of tension, and that tension is pointing somewhere, not to a single theory, not to a simple correction, but to the possibility that we are missing something fundamental, something subtle, something that does not reveal itself in obvious ways, because if it did, we would have already seen it. Instead, it appears only at the extremes, at the earliest times, in the deepest observations, in places where our models are stretched to their limits. And that is exactly where Webb is looking, deeper than any telescope before it, capturing light that has traveled for over 13 billion years, showing us the universe, not as it is now, but as it was, near the very beginning. And in doing so, it is revealing something important, not that our understanding is wrong, but that it is incomplete, that there are still pieces missing from the story, pieces that connect the beginning of the universe to everything that followed, because the early universe is not just a distant past, it is the foundation of everything we see today. Every galaxy, every star, every structure, all of it traces back to those first moments. So if something was different then, even slightly, that difference would echo forward through all of cosmic history, and that echo may be what we are detecting now, through Webb, through its observations, through patterns that don't quite align. And what makes this moment so significant is not that we have answers, it's that we have reached a point where new answers are required, where the next step is not refinement, but discovery, because something in the way the universe began, or the way it evolved, or the way its unseen components behave, is not fully understood. And that realization is where progress begins, quietly, without certainty, without immediate breakthroughs, but with a shift, a recognition that there is more to uncover, and that the universe, even now, is still holding onto its deeper secrets, not hidden behind distance, but hidden within the patterns we are only just beginning to notice. And perhaps that is the most important part of all of this, not the anomalies, not the tension, but the fact that we are now able to see them, because for most of history, we couldn't. The early universe was out of reach, unobservable, unknown. But now, for the first time, we are looking directly into it, and what we're finding is not a simple beginning, but something richer, more complex, more dynamic than we ever expected. And that means the story of the universe is still being written, not finished, not settled, but unfolding with each new observation, each new contradiction, each new question, bringing us closer to understanding what really happened in those first moments and what it means for everything that came after. Because in the end, the universe is not just something we observe. It is something we are still learning how to understand, and Webb may only be the beginning of that process.